So this is joint work with my former student, Kevin Louie. And I'm going to have to contort myself a little bit because I actually cannot see the button on the screen here. So the kind of transducers that I want to talk about today are extremely simple. So my claim would be that you can't take anything out of these guys without being left with an utterly trivial structure. So these machines here have, okay, so I may not be able to scroll down. Let's see if this works. Oh, I can actually, okay, good. So these machines take a bit stream as input and return a bit stream as output. And internally they have states, and there's only two types of states. The copy state simply takes an input bit and immediately writes it to the output. And then there are toggle states which take an input bit, flip it, and then write the flip bit to the output. And that's all there is, there's nothing else. And so here's one example of a transducer of this type. 3 states, 0, 1, 2. If you're in state 0 and you see a 1, output a 0, go to state 1. If you're in state 0 and you see a 0, output a 1, so this is a toggle state, go to 2. And 2 and 1 are just copy states. So whatever bit comes in the screen, just copy to the output, that's it. I think everybody will agree that this is a nearly trivial device. There isn't much going on, except, as it turns out, actually, it's already mightily complicated. So let me find my button up here. So, more formally speaking, if you have one of these devices, it will define a map from binary words to binary words. In fact, you get a whole bunch of maps. You can choose an arbitrary state as the initial state, and then go through this diagram, reading bits from the input, and then either just copying them or flipping them and sending them to the output. And so the one that I just showed you, if you decide to use state number 0 as the initial state, and as a notational convenience, I'm underscoring the state 0 there to indicate it's the map that you get if you start at state 0. If you feed the input string 0, 0, 0, 0, 0, 0, and so on and so forth to this device, the output is 1, 0, 0, 1, 0, 0, and so on and so forth. For human beings, it's not particularly helpful to look at these examples. You don't really see much structure there. So it's not very hard to see. In fact, it's completely straightforward to see that these maps that you get by choosing a particular state as the initial state have a whole bunch of special properties. For, in particular, the length preserving. I mean, this is trivial, right? Every time I read a bit, I write a bit. So I get a string, the output string is of the same length. But also the map is reversible. And in fact, in order to get the inverse map, all you need to do is interchange the 0, 1 labels in the transducer, and you will go backwards from the output to the input. And so if you look at the operation, at this map on the set of all words, what you really have is a length-preserving permutation. So in a sense, it's a very, very simple map. However, and this I didn't notice when I first started looking at these guys, it turns out that the nature of these maps, these permutations on binary words, is actually quite complicated. If you think of them simply as permutations, it's a very natural thing to do to consider the group that's generated by these permutations. You just look at all possible functions that you can define, not just from the maps that you get by picking an initial state, but also by functional composition. And so if you do this, you get a group or a semigroup, depending on which closure you take. And it turns out in the last 15 years or so, the groups that you can generate in this way, that you can describe in terms of these finite state machines, are the standard counterexamples for any conjecture you may have in group theory. So if you have a good idea, you can always shoot it out of the water by constructing the right group using these, these very, very simple finite state machines. And so I just mentioned one fundamental result by Grigorchuk, who actually was able to show that there's a group of intermediate growth using a transducer, just like the one that I showed you, with only 5 states. And in fact, of those 5 states, 4 are copy states. There's only 1 toggle state. And that's already enough to generate incredibly complicated groups. And it's a good thing I didn't know about this early on, because otherwise I probably I would never have touched the subject. So what I'm actually interested in is not so much the group theory. I'm interested in the automata theory. And so what I'd like to understand is what happens when you apply one of these maps over and over and over again. I'm interested in iteration. And so the first problem that one would like to tackle there is the following. Suppose I give you two words. Let's say each is 1,000 bits long. And I want to know whether one word occurs in the orbit of another. So I'll give you one of my little transducers. I fix an initial state. And now I ask you, if you apply the transduction defined by that initial state over and over and over to word X, will you ever get word Y? Now, since these are length preserving, in a sense the question is trivial. You can just enumerate the orbit and check whether the other word ever appears. But it's not very hard to see in the example that I showed you that if you start from a word of length 2n and you iterate these functions, what you get is an orbit of size 2 to the n. It's exponential. And so if you apply the brute force algorithm, it's exponential. It will take an exponential amount of time to check whether another thing appears in the orbit. And so, whenever something happens in exponential time naturally and easily, immediately the question arises, of course, can you do this in polynomial time? So just imagine you have your 2-bit strings, each 1,000 bits long. The orbit will have length 2 to the 500. So unless you find a clever shortcut, you won't be able to answer the question. I claim actually you can do it in the time that it takes your index finger to move back from the button when you input, if you do it right. And probably much faster than that even. So the question is, how hard is it to check membership in an orbit? So here's a picture of one of these orbits. If you see a structure, please let me know. I'd be keenly interested. All I see is random bits really floating around. So the starting word is there on the top left, and it just happens to be 18 zeros. And then you apply this transduction over and over and over again. And well, at the end here, the pattern is 1, 0, 1, 0, 1, 0, and so forth. If you could remember what the transducer looks like, you can check this actually in the next step will go to all zeros. I'm not lying. Indian art, okay, good. Now, how do you turn this into a theorem? I don't know. So anyway, so the idea is, I'm giving you two of these bit patterns and you're supposed to check whether they are in the same orbit or not. So how do you go about this? Let me find my cursor here. Well, so I claim it's sort of natural to try to well, okay, so here's a hope, right? I can look at the semigroup of all these transductions, and since I'm interested in iteration, well, what I'm really interested in is maps of the form f to the t for some exponent t, and those maps naturally live in the semigroup. So maybe there's some hope to get information that is helpful for the orbit problem, if only I could understand the algebraic structure of that semigroup. It's just a hope, right? If you know nothing else, you just cling to whatever seems at all plausible. And what's nice about this, approach is you can actually get some mileage out of computation because the elements in this semigroup can all be represented by finite state machines. And so I can do computation on these finite state machines to try to discover the properties of the semigroup. And so in particular, if I have, I have the finite state machine that describes these basic maps. If I want to compute a finite state machine for a composition, all I need to do is take a product construction of those automata. And the problem, of course, is with a product construction, initially I only have 3 states in my little toy machine. But if I compute a product, I get up to 9 states. Another product will give me 27 states, 81, and so forth. It grows exponentially. So you can't go very far, but at least for reasonably small compositions, you can actually build these automata and you can check whether they have interesting properties, in particular whether they're the identity, for example. And so I wrote a little program that just, by brute force, searched for interesting algebraic identities in the semigroup. And there are 2 things that fell out. This was not hard to get at all. The first one was something that I probably should have realized if I had paid attention, but I didn't. It turns out the semigroup is abelian. So all these maps commute. which is not clear if you look at the definition of the transducer, but it is a fact. So it doesn't matter whether you apply, function 0 underscore first or 1 underscore. You can always rearrange them. So that simplifies matters quite a bit. But the real discovery was this identity, which I really had no idea was going to pop up there. If you take the function that you get by moving the initial state to 0, you apply that twice. And then the function that you get from initial state 1, apply that twice. And the function that you get from initial state 2, all those together are just the identity, which you can prove computationally by just building the corresponding machine and then checking that it's equivalent to the trivial one with a 1 state. And so what that means is that I'm actually not really dealing with a semigroup, I'm actually dealing with a group, because I can have their inverses. And so I can get rid of one of the generators, and so I must live in some subgroup of z squared, an abelian subgroup, a quotient, I shouldn't say subgroup, a quotient. And as it turned out, with the computational constraints that I have, I tried very hard. I could find no other identities. This was all there was. So it seems like this is it. The semigroup is in fact a group, and it's isomorphic to z squared. However, proving that there are no other identities, of course, is much harder than just generating a few. And so I got stuck there for a while, and thank God I had a chance to talk to Knut, who immediately and totally destroyed the problem. Well, not immediately, it took him a week. So his approach to life, well, in this particular case, is if you have a hard problem that you can't solve, make it harder, and then things will happen. And so in his case, in this particular case, the idea that he came up with was to add more states to my transducer. The original transducer that I have is just 3 states. So he said, well, why not add infinitely many states? Make it an infinite machine. And all the states that you add are trivial copy states. So you can just call them 3, 4, 5, 6, 7, and so forth. And state n is a copy state, and that both transitions go to state n minus 1. So you get this infinite tail that's sticking out to the side. Why would you do this? Well, as it turns out, you can show that the semigroup generated by this infinite machine is exactly the same as the original one. So we're still talking about the same algebraic object. But in this new setting, there are more identities. In particular, there's this identity map k squared is the same as map k plus 1 composed with k plus 2. So you can replace a higher power map that uses k by a lower power maps using k plus 1 and k plus 2. I'm pushing this stuff down the tail there. And if you do this systematically, it turns out that you can rewrite any one of these transductions as a composition of the form, map k1, map k2, and so forth up to map kr, where these are all distinct. So every one of the basic functions is used at most once. You don't need 0 to the 5th, for example. You can rewrite this in a way so that all the basic functions appear only once. And if you look at the way this works, you can then easily show that, in fact, there are no other identities. So you can rewrite things. And here's just one little example of what happens. If you look at the function, so these are powers of map 0. If the exponent is 1, well, of course, there's nothing to do. You only have one map there. If it's 2, it's the second row here, then by the identity that I just showed you can rewrite it as map 2 composed with map 3. If it's 3, you can rewrite it as map 0 composed with map 2 and map 3, and so on and so forth. So this is written as a bit vector here. Here are the functions that you actually need to write map 0 to the 10th. You can always expand it, and it's a unique notation system. So there's a very nice isomorphism between these bit strings and the Gaussian integers. So this proves in particular that you have z squared. Now these normal forms, oh boy. Now what do I do? I don't think, no, sorry. Well, so here's just an attempt to visualize what happens when you calculate those normal forms. So these little columns, the number of colored blobs in the column tells you how many terms there are in the Knuth normal form, and the color tries to indicate what the actual functions are. So you can see there's obviously something very regular, right? If you go from t to t plus 1, either the number of terms increases by 1 or it decreases by 4, and there's obviously some regular pattern. Exercise, figure out what the pattern is. It's not so easy. So here's another picture which you probably will only see the half of it. Yeah, so here are all the Knuth normal forms for the map 0 to the t less than or equal to 1024. And so this is the kind of picture that strikes fear in the heart, well, in my heart at least, because there clearly is some pattern. It's just not clear what it is, right? So this should, yeah, so the first part is 0 to 256, and then it's just broken up. And it's broken up very cleverly in blocks of length 256 because it's the easiest to see the structure if you chop it this way. If you were to chop it in blocks of 300 or so, you would see absolutely nothing.
Yeah.
I mean, powers of 2 have to play a role, right? Yeah.
But the ends of the sets are chopped off.
Yeah. So unfortunately, I can't move to the side. Yeah, so there's a little bit more. There should be something more on that. You should be able to, interpolate and just figure out. Yep, so that's exactly what I said. I can kind of see a pattern, and then, a long time later, I actually had a way of describing it. Things actually get much groovier if you don't just, so this is sort of the one-dimensional case. I'm only looking at powers of map 0. But of course, we're really living in a two-dimensional world, right? My group is isomorphic to c squared. So if you try to plot a picture in the two-dimensional case, so here's one. Oh boy. It doesn't really look good at all on the screen. This is much more impressive on a good monitor. So what I'm doing here is I'm looking at all functions map 0 to the a, map 1 to the b, where a and b are on the range from, I think, minus 500 to plus 500 or some such. And what you get is a fractal. It's a bathtub fractal, which unfortunately on the screen it's hard to see. There are these components here. I can't get close to it and I lose it. Maybe it's easier to see from the audience. There are these rectangular structures that repeat on all scales. And it's very nice if you double the size, the thing rotates by 90 degrees, and after 4 doublings, you're back to the original orientation. So they're very nice. I like Knuth normal form. Okay, but so let me push ahead here a little bit. So what we have so far is a very nice way of describing these transductions, right? They're really just essentially pairs of integers, in a sense, right? I can describe them that way. And so now the hope is, given that nice description, you could actually attack this question of how hard is it to check whether a bit string appears in the orbit of another. And the right setting to think about this is to imagine that those 2 bit strings are given as input to a machine. So the machine at every time step reads 2 bits, 1 bit from x, 1 bit from y, then the next bit from x, the next bit from y. And it scans across, and as it scans, it tries to make a decision whether x occurs in the orbit of y. So what I'm really looking at is, you can think of it as a formal language, where the alphabet is not just single bits, but pairs of bits. And what I'd like to do is I'd like to build a machine which, given this input, x and y, will give me the answer yes or no, depending on whether x is in the orbit of y or not. And there is a general method. I mean, Brzozowski did this 50 years ago. There's an algorithm that allows you to construct this machine using, general principles in the theory of finite state machines. And then the question is, when you perform this construction, are you going to wind up with a machine that's finite, or are you going to wind up with an infinite transition system? And the infinite transition system is as good as useless, because with an infinite transition system, you can do absolutely everything. You can give me an arbitrary language, I can build an infinite transition system that recognizes it. So the real interesting question is, can I do this with just finitely many states? And I was totally convinced that it's impossible. If you look at the orbits a little more carefully, they have all kinds of strange combinatorial properties. And it just didn't seem right that you could build a finite state machine that would actually check whether 2 strings are in the same orbit. The orbits seem to be too complicated, and the finite state machine is just too stupid to do that. And so my battle plan was the following. I was hoping So it's always the case that if I change my problem a little bit, and instead of asking whether two arbitrary strings are in the same orbit, if I constrain the strings to have length at most n, where n is fixed, then the problem is trivially solvable by a finite state machine. Because they only find many such strings, and you can hardwire the thing into these machines. So if I constrain the length to be just n, I know there's a finite state machine. But if I don't have the constraint, my conjecture was there isn't one. So how about the following? Compute these approximation machines for a few values of n equal 1, 2, 3, 4, 5, as far as you can go. And then hopefully they will have a nice growth pattern. Actually, my conjecture was they grow quadratically. And if you can just figure out what the growth pattern is, then you can somehow prove that the big machine can't be finite. It has to be infinite. And so I went off and calculated these machines. And I drew a little picture. Here's the picture. I'm afraid. No. OK, so you still can. Yeah, it's still almost there. So this is essentially the picture that came out of Mathematica when I first did this. The only change that I made afterwards was to color the nodes blue and red, just to be, so it's easier to talk about them. But the layout was exactly what I got. So this is the machine that you get if you try to answer the question for strings up to length 17. And every column means you increase the number of bits by 1. So initially things look good. I have 4 states, then I have 7, then I have 11, and so on and so forth. It seems to be growing very, very nicely. There's a little glitch here, then it grows again. But then if you go up to 17 and you look at the picture, you realize that there's this part blue, which seems to be exactly the same as the red part. It seems that the machine has a repeating block. And so once you repeat, the hope would be that for the rest, you just keep repeating this block. But if you repeat the block, you don't really need it. You can just take the transitions that go from blue to red and rewire them back to here, and now you have a finite state machine. So I did a little surgery, and in fact, it turns out there is a finite state machine. And I can't go into details here now, but for reasons that are very hard to explain, that machine has 35 states. So I have my little 3-state transducer, and I can build with 3 states, right, just 3, but I can build a machine with 35 states that checks orbits for that transducer. And other than that, I know nothing. There is an infinite list of open problems.